Very good afternoon and warm welcome to this live session. I am Dr. Vaibhav Pandit and today we are going to see the details and the doubt for the topic that is titled the spherical coordinate system for our subject electromagnetic field theory. So here we are conducting the third live session for this subject electromagnetic field theory. The first two were for the earlier coordinate systems, those we have learned. So let us have a recap what exactly we have, and parallelly we shall be solving the doubts with respect to the spherical coordinate system, and we shall understand all the things in very details here. So the first point comes to our mind, what exactly the use of coordinate system is. So the purpose of understanding this coordinate system is that coordinate system helps us to have positioning or locationing of any of the point or a vector, which is very important to learn this subject, into a three-dimensional space here. So whatever the space we have surrounding to us, so in that space, what we call the three-dimensional space, whatever the vector quantities we require to learn in our subject of electromagnetic field theory, where few of the quantities are associated with electric field, few of other quantities are associated with the magnetic field. The behavior of both of them together we have to learn and analyze further to build the applications for the end use to benefit the human society here. So the coordinate system helps us in positioning and locating such points or vector quantities here. Now in our syllabus we have the three types of coordinate systems to learn. The first one is the rectangular coordinate system, the second one is the cylindrical coordinate system, and the third one is the spherical coordinate system, our today's topic of discussion here. Now though we have the three types of the coordinate system, the motive behind having these three types is the same, just to provide positioning and locationing to a certain point or a vector in the space. But the ways are different, hence we have the three different types. If for example we select a point P that can be mathematically denoted with the capital letter, beside it within the parenthesis we provide the three coordinate informations. So the first can be, let us say, x, then y, and then z. So x, y and z are the measures of length. So this way we can have the notation, and further the analysis we shall see into the details for the rectangular coordinate system. For the cylindrical coordinate system that we have covered, the same point P we are going to represent with rho, comma, we have phi as the second coordinate and we have z. So while we switch from rectangular coordinate system to cylindrical coordinate system, the z parameter is the same. It is the common. So as we know, x, y, z are the three measures of length. Here rho and z is the measure of length, but phi is the angle. Now come to the today's topic of discussion, that is the spherical coordinate system. While we switch from cylindrical coordinate system to this system, the representation most of the times is followed as P in the bracket. We have R, comma, theta, comma, phi here we have. So while we switch from cylindrical to spherical, phi is the common, whereas one more angle theta is added to this spherical coordinate system here. So in the rectangular coordinate system we have all the three measures of length. In the cylindrical, two coordinates are measures of length and one is the angular. And in the spherical coordinate system, just now remember that we have one coordinate as a measure of length in terms of meters, in terms of centimeters you can go for, and the two angular values here. Now we shall have a comparative study of the spherical coordinate system with the earlier ones. So let us first of all have a look on visualizing the rectangular coordinate system with the help of certain reference axis here. So for providing the positioning and location of a point or a vector in a space, we require a reference. The reference is the one which does not change its position. So it has a unique position which is referred by everyone, that is not supposed to change anytime. So with respect to that particular reference, the position and the location of any of the point or a vector quantity under our consideration is to be done here. So in the rectangular coordinate system, we have the three references. Few of the books refer that these references are the x, y and the z coordinate axis, which are mutually perpendicular to each other and they are intersecting at the point which is known by origin. Or in other words also, few of the books refer to as there are three planes which are designated with the names x is equal to 0 plane, z is equal to 0 plane, y is equal to 0 plane, and these planes are mutually perpendicular to each other. And of course, the intersection point of the three mutually perpendicular planes is nothing but the point again, which is again the origin here. So these are the three references. Now the question will come to your mind that what are the references in the case of cylindrical coordinate system and what are the references in the case of spherical coordinate system here. Now we shall move further to see how we used to have the representation of position of a simple point in rectangular coordinate system. So for example, we have taken point P which has the coordinates 1, 2, 3, point Q which has the coordinates 2, -2, 1 here. So from the point into the space, we used to simply drop a perpendicular onto the horizontal plane which is z is equal to 0 plane, or in other words we can call it to be the xy plane. So while we drop a perpendicular on this plane, here it is the point of intersection, and from this point of intersection if we draw the lines parallel to that of the x-axis which will intersect the y and a line parallel to y-axis which will intersect the x-axis, you will get these two markings correspondingly on x and y-axis. This much of distance is the first coordinate. This much of distance on y-axis is the second coordinate. And from the point, if you drop a perpendicular onto the z-axis, how much height it has attained above the origin level or below the origin level, that it is nothing but the z value. Here it is the third coordinate. So the same case we have made with respect to q also. While we have the same procedure, the line that is drawn from the intersection point parallel to the x-axis cuts the y-axis at the -2. Hence we have negation sign at the middle coordinate here. So next to that, in the rectangular coordinate system, while using the variation into the spatial dimension, as we have three dimensions here, the variation into the x dimension we represent by dx, variation into the spatial dimension y we represent dy, and correspondingly into the z we represent by dz here. So for the cuboid that we have represented in this particular diagram, if the edges are to be represented, so those edges which are parallel to that of the x-axis, as like this edge or this edge, so these are nothing but having the variations into the value of x but the constant values of the y and z. So that time we shall be representing them dx, similarly dy, similarly dz. Now when we are asked to represent a surface with the help of the rectangular coordinate system, let us say for the top surface of this cuboid, so it has one edge parallel to that of the dx as just now I have discussed about, and another which is parallel to that of the dy. To find out the surface area, we always multiply the two dimensions. Hence, the product of or the multiplication of dx and the dy is nothing but the differential surface. So this is for the top case. For the bottom surface also it will be the same. Now for the front surface from our side, This is dy into dz. Here it is the dz vertically oriented, dy here it is horizontally oriented here. And for determination of the differential volume into the rectangular coordinate system, what we do? We determine the product, the multiplication result for dx, dy and dz here. So now moving further, the simplest representation of a vector into the three-dimensional space using the rectangular coordinate system was done like this. So this is the vector. Simply we'll use a line segment. The line segment ending point we provide with the help of the arrowhead here. So here it is the starting point of the vector. Here it is the ending point of the vector. Depending on how much magnitude a vector is having, that much long line segment is to be drawn here. So while we represent it starting at the origin point, this is the end point. From this point, if you drop a perpendicular onto the xy plane and that of the z, we get the x, y and z components. Hence, any vector into the rectangular coordinate system can be resolved into the three parts as shown here. So these are just the mentions of the magnitudes here. Now we need the directions as well. The rectangular coordinate system uses the three unit vectors. So these unit vectors are correspondingly ax, ay in the small casing and az here. So these are the vectors having unit magnitude, that means magnitude is equal to 1 but directed towards the x-axis positive side, y-axis positive side, z-axis positive side here. So now our today's topic is spherical coordinate system. So the question arises, what are the unit vectors with the help of which we can have the representation and modeling in this spherical coordinate system? So this we shall compare with. Now next to that, for determination of any vector, those for example that has started at the point P and ended at the point Q here, we used to make subtraction of the coordinate values and used to obtain the vector representation in the rectangular coordinate system. Similar things we can do into the another coordinate systems also. The representation of a general vector was like this, having the magnitude components capital Bx, By, Bz and the unit vectors here. Now for determination of the magnitude, this was the formula. For determination of the unit vector value, we used to simply divide the given vector, here it is in the equation 1, by its magnitude that has been computed as per the equation number 2. So this ratio will result into the unit vector here. Now we just have a review of the another coordinate system for comparative purpose, that it is the cylindrical coordinate system. So in cylindrical coordinate system, as the name suggests, we have to imagine a cylinder that is centered at the z-axis. What is common while we switch from the rectangular coordinate system to that of the cylindrical coordinate system? So this axis is vertically oriented, upwards is the positive values, downwards are the negative values, and at the middle we have z is equal to 0. So this is basically x y plane, or z is equal to 0 plane, which is horizontal in orientation here. So now from a point P, we had dropped a perpendicular onto the z axis like this, and the length of this perpendicular segment is nothing but rho here. So imagination is to be made, considering this much of length as a radius of cylinder, we have to imagine a cylindrical shape which is centered at the z axis. So here it is the measure of length, one coordinate. Another, for this line segment, if we consider at the point of intersection onto the z axis the positive x direction, the angle measured in this fashion from the positive x towards the positive y, so that is nothing but the angle phi as shown here, and z is the common as we switch from rectangular to that of the cylindrical coordinate system. So as we have our today's topic spherical coordinate system, I just get it clear to you people, we have to imagine a spherical shape. Now let us complete what was there in cylindrical coordinate system. So comparatively we can get it more clear here. Now we have seen in the rectangular coordinate system there were the three unit vectors ax, ay, az. So those were used for the representation. In the cylindrical coordinate system, here you can see the three unit vectors, the one directed along the progression of the radial segment, here it is the arrow. The one directed along the progression of the angle phi, here it is a phi, and that is common from rectangular to the cylindrical, that is az here. So there is a question, what are the unit vectors into the spherical coordinate system, that we shall also study here. Now in cylindrical coordinate system, as like the rectangular coordinate system, we had the differential lengths, surfaces and the differential volume. So here we can have the analysis with the help of such a shape, a three-dimensional shape, which is a part taken from slicing a cylinder here. You can imagine a cylinder inside a cylinder. If this is a smaller cylinder, this is a bigger cylinder, and this is the part extracted here. So the edges, those are along the progression of the radial value are represented by d rho. Those edges which are vertical in orientation parallel to the z axis are represented by dz, and those edges which are progressing with the increasing value of the angle phi here have to be represented rho into d phi, because if the radius will increase, the length will also increase. Let us see, for the edge as a part of smaller cylinder, the length will be small as the radius is small. Let us say for example rho 1. So rho has been added with d rho here, that is why this has to be multiplied by d rho. The similar fashion is to be done here to determine the differential surfaces, the multiplication of the two. Then for the differential volume, the multiplication of the three dimensions in the coordinate system here. Now while we switch from the rectangular coordinate system to cylindrical coordinate system, we had learned the conversion among the coordinate values also. So this was the diagram which helped us to switch from both of the coordinate systems, vice versa. So this was the point P. We had dropped a perpendicular onto the xy plane, a perpendicular onto the z axis, and a part of cylinder. So we had the representation of the x component, not here. Here it is the x component. Here it is the y component, the z component, the height attained from the level of origin, and the rho component, phi component and z component. So all the parameters for both of the coordinate systems were shown in a single diagram, and by using the rules of trigonometry as like the cosine and the sine ratios and the Pythagoras theorem to determine the length of the hypotenuse in a right angle triangle, here we had the conversion formulas. So while we try to have a conversion from cylindrical to rectangular, it means when we are known to the values of rho, phi and z, we should be able to determine the values of x, y and z. So for that purpose, to look at the geometry of the triangle, we had derived the formulation that x is nothing but rho times cos phi, whereas y is nothing but rho times sin phi, and z is the same as it is common to both of the coordinate systems. The reverse coordinate conversion we had also seen, that it was rectangular to the cylindrical coordinate system. When we are known to the values of x, y and z, we should be able to determine the values of rho, phi and z, from x, y, z to rho, phi and z. So for that purpose, we had from the Pythagoras theorem, rho is equal to the square root of x square added with y square, provided rho is greater than or equal to 0. When rho is equal to 0, it won't be a cylindrical surface like this. It will be simply a line here. Now the next conversion we had with the help of the formula by taking the ratio of sine and the cos. Here it is phi is equal to tan inverse of y by x, and finally z is the same here. So in both of the coordinate systems, rectangular and the cylindrical coordinate system, we have shown the representation of a vector onto the plane of the mathematical tools here, operators here. So for the Cartesian, which is also called as the rectangular coordinate system, we had this representation in general: a is equal to ax added by ay added by az. And in the cylindrical coordinate system, we had this representation where we have arrow into arrow, a phi into a phi, az into az, and the determination of the vector representation when it is given in one coordinate system to the another coordinate system, those problems were also solved. Now, with this much of proper understanding, we shall have every detail of the spherical coordinate system. So, what is the reference into the spherical coordinate system? So, in the spherical coordinate system, we have the reference as a single point. Now, remember, while we switched from the rectangular to that of the cylindrical coordinate system, earlier we had the three references x, y and z coordinates. So x-axis, y-axis, z-axis, they were mutually perpendicular to each other, and it was preferred to use the right-handed coordinate system. Now while we switched to the cylindrical coordinate system, we were left with only one reference, that it was nothing but the z-axis. X-axis and y-axis, those were not needed much. Now while we are in spherical coordinate system, we require only a point which is origin. So origin, we have talked about the intersection of the three axes x, y, z. Those are required to have the rectangular coordinate system into the use, or the intersection point of the three planes x, y, y, z and x, z. So this is the reference point, and with the help of this reference point, let us have the positioning and location of first of all a point and then a vector using our current topic, that is spherical coordinate system. So here we have the origin O located at the center here. Now we have imagined the three dimensions from the rectangular coordinate system also, x, y and z here. Now the point P is the same. Now this point P we have to represent with the help of spherical coordinate system, as earlier we had shown to you that in brief, that P in the bracket r comma theta comma phi. So what is r? When we join the position of this point P with the position of the point O, which is origin, the intersection of the three axes, so that line segment we have to imagine as a radius of a sphere. So when you have the three axes like this, you have to imagine a sphere. So this sphere is centered at the origin here. So from this sphere, when a portion has been sliced, which is into the positive quadrants of the xyz axis, this has been shown here. So this is the line joining from point P to that of the origin. This is regarded as the radius of the sphere, and it is denoted by small r here. Now the angle made by this radius segment at the considered point P with the positive side of the z axis in the progression like this is nothing but the angle theta, and phi is the common as we switch from the cylindrical coordinate system to that of the spherical coordinate system. So here what we need to do, we have to drop a perpendicular onto the z axis. At the point of intersection, we have to imagine the positive x direction, and the angle measured from the positive direction of x towards this perpendicular line segment is nothing but the angle phi here. So with the r and phi, we have another angle, that it is theta. So this is the simple introduction to the spherical coordinate system here. So now we shall discuss about the three different kinds of planes those are associated to this coordinate system. In the rectangular coordinate system, we had xy, yz and xz plane. Those can be simply called upon as z is equal to 0 plane, y is equal to 0 plane, x is equal to 0 plane. In the cylindrical coordinate system, the planes are not exactly having the straight orientation, but one plane is cylindrical in nature, so that it was rho is equal to certain constant. Another planes as like z is equal to 0 is a horizontal disk. Now in spherical coordinate system we shall see in the details with the help of this visualization. So in this visualization, at the center, that is the intersection of the three axes, we have imagined O. So from this origin O, whatever the radius segment is there up to the point P, with this much of radius R, as we have shown earlier, whatever the spherical shape we get here, this is nothing but R is equal to certain constant value that can be here denoted by small a also. So here it is a shape of sphere, a part of the sphere, spherical surface here we have. Now when we limit the values of theta to a constant value, let us say theta is equal to small a, either you mention it in the terms of degrees or in the terms of radians. So what will happen if you try to extract a portion from a complete sphere, you will get a cone here. I will explain you onto the side here. So this will be the cone, which is a part of a sphere. So here it is, the cone. So this point is nothing but the origin O. So out of a sphere we have this vertical orientation of the z axis, and every point that is lying onto either this periphery or in the body of this particular cone, which is hollow inside, will make the same angle theta, which is having a constant value. So this is nothing but the conical surface. So the first surface we have a spherical surface, the second surface we have a conical surface, and the third surface. The third surface, phi is equal to constant. Phi is common from the cylindrical coordinate system to that of the spherical coordinate system. Phi is the angle measured into the horizontal plane like this. So if you limit the value of the angle phi to a constant, so that time we shall collect all such points which have the constant angle phi from the positive x direction. It will be a vertically oriented plane, and that plane will make the angle phi is equal to constant with the positive x direction here. So out of the three surfaces here, one is spherical, another is conical, and the third one is a plane or a straight surface here. Now these are the surfaces in the spherical coordinate system. Now what are the three unit vectors with the help of which we have the mathematical notation for the representation of a point or a vector into the three-dimensional space using this coordinate system, that we shall see here. So I hope it is very clear the spherical structure, the spherical shape into your mind, that is origin at the point O, and it has the radius denoted by R here. So when we take a unit vector that is directed into the progression of the radius of the sphere, the unit vector is to be denoted by small ar here. When we take a unit vector into the direction of progression of the angle theta, so this way the downwards we measure the angle theta. So a tangent to that particular path is nothing but the a theta unit vector here, and the unit vector which is in the direction of progression of measurement of the angle phi here, in this particular way we have a tangent to that particular path, that it is nothing but the a phi unit vector here. So in rectangular coordinate system, which has another name also, it is also identified by Cartesian coordinate system. We have the unit vectors small casing ax, ay, az. In the cylindrical coordinate system, we have a rho, a phi, az. And in our current topic of discussion, that is the third coordinate system, the spherical coordinate system, we have AR, A theta, A phi here. So the two unit vectors are tangential to the paths through which we measure the angles theta and phi here. Now one more question regarding the entire range of values we can measure for these particular parameters r, theta and phi. If you talk about r, so r is the radius of sphere. So the radius of sphere, we can start at the 0. It is basically a point here. So if you increase the value of r from 0 to positive infinity, you can get bigger and bigger and bigger spheres in this fashion. So r is equal to, let us say, some small value, r is equal to bigger value, bigger than that. So you can imagine a sphere inside sphere inside sphere. So that way you can have r is equal to 0 to positive infinity. It can't be the negative infinity. For the angle theta, as you are measuring it right from the positive side of the z, which is having the upright upward orientation here. So the measure of angle, of course, for the radius of the sphere is in the downwards fashion here. So you can extend up to the negative z direction, that is the downwards here. So the range of theta value is 0 degree to that of the 180 degree here, or pi radians here. And for the phi, you can have the measurement of the angle in this particular fashion. So it will make 360 degrees into the horizontal plane, that can be xy plane if you talk about the rectangular coordinate system here. So the unit vectors we have talked about, the range of the three parameters we have talked about. Now let us have the conversion of the coordinate values from one system to another system. So with the knowledge of the spherical coordinate system, we have in total the three coordinate systems. So into the examination, most of the times you are provided the coordinate values in one system and you are asked to determine the values for representation in the another one. So let us take for example, we have the spherical values and we require the rectangular values to be determined. So you should have the formulations x, y, z in terms of r, theta and phi here. So for that purpose, we get back to our one diagram where we had represented a point here. But before that, we shall briefly discuss about the differential length, surface and the volume associated to the spherical coordinate system. So if we take out such a part out from the spherical shape here, first of all you can imagine a sphere inside a sphere, and then you can slice out this particular portion. So you will get different edges. So those four edges which are directed into the progression of the radius segment, these are definitely represented by dr. Now those edges which are in the direction of progression of measurement of the angle theta right from the positive z side downwards here are represented by r times d theta, because if the radius of the sphere will increase, the length of such edges will also increase. And when you have the progression alongside the measurement of phi angle, we have already denoted it into the cylindrical coordinate system by rho times d phi here. Now we are dealing with the spherical coordinate system, we cannot make the use of rho here. So we have to get the rho converted and represented in terms of the rectangular coordinates r, theta and phi. So we get it to know that rho is nothing but the r sin theta. So how that we shall see. Now here we have the earlier diagram where we had shown the point P into the space. So here it is the point P. Now here it is the position of origin, the intersection of the three axes x, y, z in the rectangular. Here it is our radius segment that joins the point P to that of the origin here. The angle theta measured from the positive z direction to that of this radius segment r, and the angle phi. So when you drop a perpendicular point of intersection here, if you take the positive x direction, that angle is nothing but the phi here. So now what we shall consider, we shall have a perpendicular onto the z axis. So if this is a perpendicular, consider the symmetry of the diagram while drawing here. Here it is the right angle. Now if you consider a vertical edge of this triangle, the radius segment of the sphere r and the perpendicular that has been dropped, this is nothing but a right angle triangle. Now the perpendicular that we drop onto the z axis like this at this point is nothing but the imagination of the rho segment, which we consider to be the radius of the cylindrical shape here. So for this side of the triangle, the edge is represented by rho. This edge is represented by r, and as we know, whatever the height a point attains above or below the origin in the positive or negative, we have to represent the dimensions by z, and of course it is onto the z axis. So for this triangle we have the three edges. The first side edges we denote by rho and z here, and the hypotenuse, which is the edge opposite to that of the right angle, is nothing but the r here. So here what we need to do, we shall be making the use of Pythagoras theorem. So the square of the hypotenuse is nothing but the addition of the square of the two side edges here. The next thing, here we have one angle, here it is the theta here. Now we can make the use of the sine angle and the cosine angle. So for sine angle, what we shall do, we shall have the ratio of opposite side divided by the hypotenuse here. So for theta angle here, the opposite edge is nothing but the rho here. So rho divided by r is nothing but the sine theta. If you take cosine theta, it will be z divided by r here. So in that fashion, we get to know that rho is nothing but r sine theta, as we had earlier shown to you people. Now with the understanding of this much of geometry, with the help of the right angle triangle that just now we have seen, and the another right angle triangle as we had in the case of conversion from the rectangular to that of the cylindrical coordinate system, here we shall have the conversion formulas while we switch to spherical to the rectangular here. So we have x is equal to, as we had in the case of the cylindrical coordinate system, x is equal to rho cosine of phi here. So while we substitute rho value to be the r sine theta, we get x is equal to r sine theta cosine phi. In the similar fashion, y it was rho sine phi. So with the substitution of rho is equal to r sine theta, as just now we have seen, we get y is equal to r sine theta sine phi. And finally, the z can be denoted as z is equal to r times cosine theta. Just now onto the previous slide, with the help of diagram, we had the cosine of theta is nothing but z divided by the hypotenuse r. So r we can shift onto the another side, which will result into z is equal to, we have r times cosine of theta. So onto the right hand side, if you are known to the values of spherical coordinates, r in the terms of meters or centimeters, theta and phi in the terms of degrees or radians, that means you have a knowledge of the spherical coordinate values, then you shall be able to determine the values of x, y, z and express the given details in the rectangular coordinate fashion here. Now we will try to get this reversed. So for that purpose, we have a coordinate conversion from rectangular to the spherical here. So we expect that we know the values of the x, y, z, and we try to determine the values of the r, theta and phi. So as we shall see here, R is the hypotenuse of the right angle triangle we had discussed. So the two side edges are the z and the rho. So r is of course the square root of the rho square plus z square. But rho is the hypotenuse of the triangle where the two side walls are x and y. So we can express directly r square is equal to the addition of x square, y square and z square, and the r component can be computed as the square root of the right hand side. Now, provided the condition R, of course, is greater than or equal to 0. So, basically, R is equal to 0 will be a simply point, not a sphere here. And there won't be any XYZ values. So, now, when we require to make the computation of theta after this R, we have to take the help of the trigonometric cosine rule here. So if you determine the cosine of the theta, so it is definitely z divided by the r. Now the r we have determined in terms of the rectangular coordinates x, y, z here. So if we make the substitution and get the theta isolated onto the left hand side, we will get to a formulation that theta is nothing but the cosine inverse of the ratio where the numerator is z and the denominator is r, substituted by the square root of x square plus y square plus z square here, provided the range of theta is mentioned here, that the lowest threshold value is 0 degrees and the highest one is 180 degrees. So 0 degrees correspond to the positive z direction and 180 degree correspond to the negative z direction here. So now we are successful to have the conversion of the two coordinates from rectangular to the spherical, that we have obtained the equation for r here as well the equation for theta here. Now we shall require the equation for the third spherical coordinate, that it is the phi here. So for the case of phi here, we have the use of the tangential ratio here. So it is the same formulation. If we get back to the cylindrical coordinate system, phi is nothing but the tan inverse of y by x here. So this is also derived from the right angle triangle that we had discussed while we switch from the rectangular to that of the cylindrical coordinate system. Now associated with the cylindrical coordinate system, there it is a question from one student, wisdom vehicle. The question is, why cylindrical system is needed? My dear friend, the question is answered at the beginning of this session, that any coordinate system you take, either you take cylindrical that we are talking about, or the spherical, the today's topic, or the earlier one, the rectangular coordinate system. These coordinate systems provide us the use of different references, and with the help of these references we can show the position or location of any point or any vector quantity into the space on a plane of paper. Okay, so of course the symbols and the mathematical operators we need to take into the use here. And one more extended question to yours can be, why we require cylindrical and spherical when we have the rectangular, the simplest one to understand, as we have the three directions, the straight directions here. Because naturally existing information, what we call the information is a signal. The variation of the values can be into the curvical fashion here, the arc fashion here, or it can have the different ways here. So depending on the behavior of the variations, what we currently take to be the edges of the differential length, surface and the differential volume, what we have talked about in that particular extract. So these variations cannot be always the straight here. They can have the angular terms into the use for analysis purpose. So as per the convenience, we can select any of the three here. If all the directions are into the straight lines, you definitely prefer the rectangular coordinate system. When the shapes are into the form of the cylinder, you can be convenient to use into the cylindrical coordinate system. Instead, if you go for the rectangular, much more steps it will need to make the computation required, which can be simply derived with the help of very simple formula in cylindrical coordinate system. And as well the case into the spherical also. If you have something, a model that is of spherical shape, so it won't be preferable to get all the things first of all analyzed into this rectangular coordinate system, cylindrical coordinate system. So depending on what application model you are working with, the suitable coordinate system is to be selected, which enables you to provide location or positioning of any of the point or a vector quantity here. Because afterwards, while we move deeper and deeper in this particular subject, electromagnetic field theory, for electric field we have to learn the behavior of the electric field intensity, electric flux density. For magnetic field, respectively, here we have magnetic field intensity, magnetic flux density. So that time we require all these things. That is why the first chapter, the first unit for the subject electromagnetic field theory is the vector algebra, and there we need to require to study all these coordinate systems here. So now with this answer we shall move further into the details of the spherical coordinate system, where we can have the use of the dot multiplications, the combinations for the rectangular and that of the spherical coordinate system. Because with the help of the earlier 6 formulas for xyz in terms of r theta phi and for r theta phi in terms of xyz, we can have the conversion from rectangular to spherical, spherical to rectangle, and also even with the earlier knowledge we can switch to the cylindrical coordinate system. While having the representation of a vector shifted from one system to the another system, we have to make the dot multiplication into the use. So for that purpose this table will help you a lot. So here into the first column, here we represent ax, ay, az in small casing. These are the unit vectors, and in the first row we have ar, a theta and a phi. While you consider the directions of progressions of these quantities r, theta and phi along with xyz, we have these dot multiplication resultants tabulated like this here. So for example, if you take the az dot of ar, so from the third row with the first column, if you derive it onto the geometry of the diagram that we have just now discussed here, it will come to the value cosine of the theta, and this has been tabulated here. If you go for az dot of a theta, you will come to have minus sine theta, that has been tabulated as the second cell in the last row here, and az dot of a phi, as they are having the 90-degree angle with each other, az oriented vertically and a phi that is lying into the horizontal plane here, they make 90-degree angle, so you get that value to be equal to 0 here. So this will definitely help us to solve the problems associated with the spherical coordinate system. Those are usually asked into the examination. We shall briefly have a practice of the 3 problems here. So first of all, we take the problem statement where you are asked to show that the vector fields are everywhere parallel to each other. So in this problem statement, the 2 vector fields are given to you, and these vector fields are expressed in the spherical coordinate system fashion here. So if you take the rectangular, as like you have capital AX into small ax added by capital AY small ay added by capital AZ small az. So the small casings are the unit vectors. So here in this representations you will find the unit vectors AR, A theta here. So while you see the theta, so you have to guess that this is from the spherical coordinate system. So theta is associated with spherical coordinate system only. It is not there in the cylindrical or it is not there into the rectangular here. So as a part of this vector representation, you have this much of magnitude, that sine of twice theta divided by small r square, and it is multiplied by the direction component unit vector ar. So here you have capital AR into small ar. So these parentheses that I have drawn is capital A suffix small r you can draw here. Whereas in the second term onto the right hand side, twice of sine theta divided by r square, if you take, here it is the magnitude, and if you take out this a theta outside, here it is the direction component unit vector here. So we have the two parts for the vector A represented in the spherical coordinate system, and as well for vector B represented in the again spherical coordinate system. Here we have the AR unit vector and A theta unit vector here. Now we are asked to show that these two vector fields are everywhere parallel to each other. So for that purpose, let us find the solution where we take the help from a cross product here. So cross product we have already discussed a lot of times right from the first session. So the cross product between the two vector orientations taken into a plane of paper in the two dimensions simply we can take. So can be represented by A vector cross notation B vector as we are doing it here. So we have to solve a determinant, the simplest formula to derive the resultant of this cross multiplication here. So that time you will come to see a magnitude along with the angle here. So the angle can be determined by the help of the right hand thumb rule depending on the constituent, the unit vectors here you will get it calculated here. So the magnitude here we are obtaining sine twice theta divided by r minus twice sine theta cos theta divided by r, and to this magnitude shown into the parenthesis a phi is multiplied as the resultant angle here. So if you get this solved, you will come to see the value to be equal to 0 here. So if we compare it to the formulation of the cross product here, the cross product is always determined for the first vector, the magnitude multiplied to the magnitude of the second vector. Here we are showing mod A, mod B here, and the sine of the smaller angle theta between them, and along with the normal direction, the perpendicular direction to the plane in which the A and B are lying here. So if you compare this to the parent formula, we will come to see that the direction is determined, and that we come to see that here n is nothing but a phi. Now as we see, then the magnitude is equal to 0, so it means sine theta is of course equal to 0. And when do the sine value for any angle comes out to be equal to 0? Then and then only when we have theta is equal to 0 here, or theta is equal to 180 degree, or theta is equal to 360 degree. So if we consider theta is equal to any of these three values, 0, 180 or 360, which is nothing but the 0 degrees here, we can conclude that the given vector fields A and B are everywhere parallel to each other. So this way we have solved this particular first problem. Now let us have another problem for practice purpose. Let us take the problem statement where we have the statement starting as like transform the vector field from cylindrical coordinates to that of the spherical coordinates. Now the vector field is given to us, it is represented as capital H is equal to capital A by rho in multiplication to A phi. So we have been given this particular vector field. While you look at the mathematical expression of the given vector field, first thing is to do that to see what particular unit vector is involved in its representation. As we see A phi, so you can come to see that phi is the thing in cylindrical coordinate system as well as in the spherical coordinate system. Other than the A phi component, there is nothing as such AX, AY, AZ or AR or A theta. So It is of course there in the cylindrical coordinate systems, and while we switch to the spherical coordinate system, the unit vector is need not to be changed here. Only we have to change the magnitude part. So let us discuss it. So while answering this, the unit vector is need not to be changed. While capital A is shown to us, capital A is a constant value. It can attain any value as like 5, 10, 100, 11, and now we need to only express the radial segment into the cylindrical coordinate system, that it is rho, which is lying at the denominator of the cylindrical coordinate system, into the spherical coordinate system. So as just now we have gone through the conversion formulae for cylindrical to that of the spherical, we can take rho is nothing but r times sine theta. So this is the formulation we have derived from the right angle triangle that we have seen in the geometry of the figure. So while we substitute rho is equal to r sine theta, the given vector field can be denoted, can be expressed into the spherical coordinate system. So for the determination into the spherical coordinate system, here within the parenthesis we represent r comma theta here. H is the same vector field. On the RHS we express everything into the spherical coordinate system. A constant divided by r sine theta in multiplication to the a phi unit vector. So this is the required answer for this particular problem statement here. Now along with this we shall take the last problem for the practice purpose. Here we start this particular problem statement with express the uniform vector field in the spherical components here. Now the given vector field is given to us, is provided to us. Here it is expressed as capital F is equal to pi u times small casing AX here. So as we had discussed, once you see the mathematical expression representing any of the vector field, you have to first of all focus on to the unit vector involved in its representation. Here we have it AX here. So you can identify that AX is the unit vector in the direction of positive x-axis. So this belongs to the representation of rectangular, also known by Cartesian coordinate system. So from the rectangular coordinate system, to accomplish the given task, we have to switch the spherical coordinate system. So for the same, we have to take the help of the dot multiplications here. So for example, capital F expressed into the rectangular coordinate system, it can have the components as capital F suffix x into small ax, the unit vector, added by capital F suffix y in multiplication to the small ay here, the unit vector, added by capital F suffix z into the unit vector az here. So in the given expression we have fy component to be equal to 0, fz component is also equal to 0. We have only the fx component. Now as we are required to express it into the spherical coordinate system, we shall be expressing capital F as we take capital F suffix small r into small ar cap here, or simply ar vector. Then we can have f suffix theta into a theta, the unit vector, into added by we can have f suffix phi in multiplication to a phi component here. So to express this in terms of capital Fr, capital F theta, capital F phi, we need the dot multiplications here. So now the representation as we have in the rectangular coordinate system is to be perform the dot multiplication with the unit vector AR. First of all, to determine FR, we get phi u sin theta cosine phi. In the similar fashion, F theta can be determined by having the capital F represented in the first equation, dot multiplication with E theta. It will result into phi u cosine theta cosine phi here. Then f phi is equal to phi u times ax from the first equation into a phi. It comes to the result minus phi u sine phi here. So these are the three magnitude components along the r direction, theta direction and phi direction. If you collect these magnitude components and also express them with the help of unit vectors directed along small r, theta and phi, the direction of progression, we have the resultant representation, that is the required one. Here we have onto the left hand side capital F, within the parenthesis we have spherical components into the use, into the consideration hence, and by the final answer we take out the phi u outside as a common. Within the bracket here we have the first component sine theta cosine phi AR added by cosine theta cos phi A theta minus sine phi A phi. So this completes the required answer. So I hope I have covered every detail with respect to the spherical coordinate system. Always remember while learning the coordinate system what exactly the references are there, with respect to which we have to provide the location or position of a certain point first of all, and then study the vector. That is of the most important here. And as the curvatures bring little bit of the complexity into the diagram here, we have to take the help of the trigonometric rules here. So with the trigonometric ratios for the concerned angular component here, we can have the conversion formulae derived. The conversion formulas are not to be mugged up. They can be derived at a time just by imagining in which particular directions the given vector fields from the problem statement are oriented here. Thank you.